All right, we're going to talk about cubic and cube root functions. They're uh, they're structured very similarly to what we were doing with the absolute value, the quadratic, and also the square root functions. So if we're looking at the parent function for the cubic, that's the power of 3, it would be in the form of y equals a times x minus h to the third power instead of the second power plus k. And for the cube root, it would be y equals a times the cube root instead of the square root of x minus h plus k. And what we learned about, or reinforced, discussed, when we talked about those other types of functions, was get to know the parent function, and everything else is just a transformation from there. Page 15. So that's what we're going to do first. We're going to look at a table of values for the cubic, which is y equals x to the third power. Now, you may want to get a calculator involved for some of it, but other parts of it, maybe not. Like these entries here, -2, -1, 0, and 1 and 2. Those you should be able to do by hand, but the number of times I've seen a person write 2 to the third power equals 6, it's too many to count. And if you're thinking to yourself, what's wrong with that? Well, what's wrong with it is that that's not what 2 to the third power is equal to. Because 2 to the third power is 2 times 2, which is 4, times 2, which will give you an 8. Exactly. Bless you. So if you're worried that that's a you kind of mistake, like every now and then I'll see a mistake and I'll be like, yep, I'm going to make that one, then get the calculator involved. The cube roots, same deal, just going the other way. Worst case scenario, get the calculator involved, let it do the computations, and save yourself a little bit of angst. All right, so just wait the obligatory half an hour for the calculator to open up. Oh, just another 29 minutes. Oh, there we go. Okay, good. A new world record. So you type in x to the third power, so the caret key. Why they call it a caret, I have no idea. X to the third power. Second graph brings you to the table. And then you can get the important values. All right, so starting with -8, then we skip a few, we get the -2, -1, -2 gives you a -8, -1 gives you a -1, 0 gives you 0, 1, 1, 2, 8, and 8 will give you a 5, 12. All right, so we can get those values in. Oops. -5, 12, -8, -1, 0, 1, 8, 512. Then for the cube roots, if you know them, that's great. Otherwise, y equals. Now, there's two ways, well, actually, there's three ways to get a cube root in your calculator. One would be to raise whatever your expression is to the 1/3 power. So type in power of 1 over 3. All right, when you put in a fractional exponent, the denominator is the root, the numerator is the power. So this is saying take x, raise it to the first power, so no change there, and then take the cube root. So the calculator understands that. You don't want that, you go into math. Your choices are option 4 or 5. If you go to option 4, that's the cube root. Done. Type in the x. But you may be concerned, what if I have like the 8th root or the 7th root or something like that? You know, because this idea of function notation seems to have no end. And spoiler, it doesn't. So you could type in math option 5, that's the any root, and then you could type in whatever the index is. So let's say you wanted the 8th root. You put in the 8th root there. But we want the cube root, so I'd put in a 3, put in the x. Now I have the cube root function. All right, so a bunch of different ways to do it. Lots of decimals. Ignore all those. 8 gives me a 2. 1 gives me a 1. Oh, sorry, ignore. 1 gives me a 1. 0 is a 0. -1, also -1. -2 gives me a decimal, ignore it. -8 gives me a -2. All right. So you can get your parent function from the calculator. You could actually get the entire graph from the calculator, but I find it's a little bit more straightforward to plot the parent and then see how everything relates to that parent. All right. So looking at the first graph, we have 1/2 x to the third power. So I'm going to focus on the cubic, y equals x to the third, that parent function. Obviously, I'm not going to plot -8, -5, 12. That's going to go off the grid. I could scale it, but then I wouldn't be able to see all those other little points. So I'm going to ignore those. I'm only going to focus on the reasonable values. All right, so -2, -8. Right here, -1, -1, 0, 0, 1, 1, 2, 8. That's my parent function. I'm going to write it as y equals x cubed because I already have f of x here. I don't want to get the wires crossed. All right. I don't see an h and k value. I only see an a value. The a value is 1/2, so I have a stretch factor. Well, actually, in this case, it would be a shrink of 1/2. So I'm going to take each of my y values, chop them in half. All right. 0's not going anywhere. This y value here at 1 will now be at 1/2. This y value here at 8 will now be at 4. All right. -1 goes to -1/2. -8 goes to -4. All right. So these are my new important values. So -4. Well, it'd be too hard to get -1/2 in there, but +4 instead of 8 and -8. All right. Then I connect those points with a smooth curve, but you'll see that it kind of merges with the original graph. That's okay. With higher order polynomials, so when the powers are really large, or as they get larger and larger, the graph tends to get steeper and steeper, right? With a lot more bumps along the road. So there's a lot of steepness going on in these graphs, so it's likely that they'll merge with one another at some point, all right, and intersect. So we're looking at something that looks like this, and that would be my f of x. All right. I realized after the fact that I didn't have an example that had all the ingredients, so I'm going to change number 3. All right, so this is a typo for somebody. Let's make the leading coefficient here a -2, and let's throw a +1 on at the end. All right, so -2 parentheses x minus 2 to the third power plus 1. All right. So we have a negative value. That's a reflection over the x-axis. All right, we have a 2, which gives us a stretch factor of 2. H and K, you got an H value of 2, a K value of 1. That's telling me to shift right 2, up 1. All right, so I start with my parent function, which I did not copy and paste. Let me see if I can Copy. Same set of special points. All right, -1, -1, 0, 0, 1, 1, 2, 8, -2, -8. All right, I'm going to take each one of those values and flip them over the x-axis. All right, 0 is not going anywhere. But -1, -1 is going to go to -1, +1. 1, 1 is going to go to 1, -1. -2, -8 is going to go to -2, +8. Then 2, 8 is going to go to 2, -8. All right, so all I'm doing is flipping those points over the axis. Then I got to do a stretch factor of 2. So I have to double the distance each point is away from the x-axis. All right, so each point is based off of the parent function, but I already reflected them, but the distances are still the same. All right, so 1, -1 is now going to go to 1, -2. 0 is still staying at 0 for now. -1, 1 is going to -1, 2. But these points are going right off the grid. All right? So there's really not much we can do with those, except to use them as anchor points. So get an idea of where those points would be. So it'd be somewhere over in this neighborhood. It really just gives you a sense of what to aim for. All right? But we're really going to do all the magic here using the 3 points that I just indicated in orange. All right, we're going to shift those points to the right 2 and up 1. So right 2, up 1. Right 2, up 1. Right 2, up 1. And again, not much we can do with the high points, the high and the low, because they're off the grid. But we do know the neighborhood of where they would end up if the grid was much bigger. All right, so I have the 3 special points here, and I know that it's going to be pretty steep. So I can create my graph. It's going to look something like this. And that's really all we could do. We call it h of x, and we go on about our business. All right. With cubic functions, you think about, like, for example, if I take 2 and raise it to the 3rd power, not a big deal, it becomes an 8. But if I take 5 and raise it to the 3rd power, it becomes 125, which is really far away from the x-axis. All right, if I take that value and double it, okay, it's double, but it's still, in my mind, I'm looking at it as really far away from the x-axis. Nothing in my mind has really changed. All right, so that large number tells me steep graph. All right, when you think large values that you're plotting, the curve must be fairly steep. All right, unless they're really spaced out horizontally, but that's not the case here. All right, and really a lot of the point behind these transformations is to get you a sense of the visual aspects of these functions. Not just, I put it in the calculator, this is what it looks like. It looks like this because, of course, it looks like this. Right? Because this is what the parent function looks like. And if I move the parent function left, right, up, down, flip it around, rotate it even, this is what it would look like. Right? Because I know a lot about the parent function. Right? That's well, it's obvious. That's where I'm at, but I'd like you to get there too. All right. So then the next type of function is the cube root function. We plot the parent, 0, 0, 1, 1, 8, 2, and then same deal going the other way. This is coming off of the second table. All right, so this is y is equal to the cube root of x. All right, so we already did the cubic function. Now we're doing the cube root function. All right, same characteristics as a cubic function, except it's flipped on its side. There's actually more to it than that. It's an inverse of the cubic function, but just thinking of it as a rotation kind of gets you an idea of what's going on. All right, here we have a stretch factor of 4. Which means take each of my y values and multiply them by 4. All right, 0's not going anywhere, but 1 goes to 4, 2 goes to 8, -1 goes to -2, -2 goes to -8. And these would be my new points. So you're looking at something like this, and I think it's fairly reasonable to look at it and say, yeah, that kind of looks like what would happen if you stretched out that black graph. Forgot to open the Zoom. To change up a little bit, let's give it, well, I'm just going to rewrite it. M of x is equal to, let's say, -3 times the cube root of x minus 1 plus 2. All right. And really, honestly, when it comes to any kind of function, with the standard form, you really just need to have the parent function, because everything else is just going to be a movement from that. So worst case scenario, just go into your calculator, type in the parent of the function, in this case the cube root of x, and then look at the picture. Or, you need points, so zoom 6, you look at the picture. If you can get the points out of this, congratulations, you're better at this than I am. Second graph to get some nice convenient points. Now you'll see that there are more than a few convenient points, but -27, -3, convenient numerically, as in it's not decimal, but convenient graphically. I don't want to scale it by like 9s or 3s or whatever, so I'm going to ignore that one. I would plot -8, -2. All right, so this is where I would get my parent function points. If I didn't know them off the top of my head. Then I'd go down the line, I see -1, -1. This is all in the table on the previous page. 0, 0, 1, 1. Then skip all the decimals. You can plot them if you want, but it makes things complicated. I lost track. 1, 2, 3, 4, 5, 6, 7, 8. 8, 2. All right. So that's my parent. All right. So same thing I did with the previous problem, except I didn't take the points for granted. I'm like, I'm a little iffy on what the points are, so I just chuck it in my calculator. All right. But I have a reflection over the x-axis. All right. I have a stretch factor of 3. And I got an h value of 1, k value of 2, so shift right 1 up 2. I always take care of reflections first, then the stretch, and then any kind of shifting. All right. So looking at my points here, 0's not going anywhere for the time being, but 1, 1 will go to 1, -1. 8, 2 will go to 8, -2. -1, -1 will go to -1, +1. Basically just flipping right over to the other side of the axis. All right. Then I'm going to stretch by a factor of 3. So these points, their distances from the x-axis is going to get tripled. So this one's 2 units away. I want it to be 6 units away. So 3, 4, 5, 6 units. This one's 1 unit away. I want it to be 3 units away. 0's not going anywhere. 1 goes to 3. 2 goes to 6. All right. Then I do my shifting, right 1 up 2. So right 1 up 2 for each point. All right, and then I just plot. So new point here, 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 and here. Connect it with a smooth curve, and you have your graph. Then that would be our m of x. All right. All those little points and markings, you don't need to have those. That's just really for your benefit, note-taking purposes. But you know, if you want to include them, that's fine. Just be careful. I got like, I don't want to say infinitely many colors to choose from, but I got a lot. Usually I have like 1 or 2. All right. So just be careful that you don't get your points confused. All right. But that's really it. So your assignment is going to be to complete page 17 and submit on Schoology. There's only a few problems. It doesn't take too long. So for the first, and well, out of the graphs, the first and the fourth one, those are the cube root functions, the ones we just did, and 6 and 7 are the cubic functions. So for that, let me get the calculator out of the way. You'd go back and take a look at what we did over here. All right. So, and it all starts with the parent function. Right. So you get the parent function. Like again, just very quickly, if I want the parent function for the power of 3, x to the 3rd power, go right to the table, grab some convenient points, plot them, then start your transformation. Shift left, right. You know, reflect, stretch, shift left, right, up, down. All right. So I'm going to